Today we're going to talk about production line audio testing. A lot has changed over the 30 years we've been in business. When I started Listen, customers tested loudspeakers on the production line with a human listener. They would play a sign sweep through the driver, listen to the output, and make a subjective judgment on whether it sounded good. Back then, labor was cheap, especially in China, and my biggest sales challenge was convincing a customer to invest in an automated test system. I had to convince customers not only that the automated test systems could identify faults as well as humans, but also that they were faster, more reliable, and would be less expensive in the long run. Today, automated testing is standard worldwide. Everyone's doing it, except a few high-end loudspeaker and headphone companies who have small production runs. It's not just loudspeakers. We're also talking about headphones, smart devices, microphones, multifunction devices, and more. The devices have gotten more complex, so the testing needs to as well. For example, we need to deal with different fixturing, communication protocols like Bluetooth and A2B, haptic measurements, and more. With some of these devices, audio measurements are just a small part of an overall end-of-line test that might include optical inspection, mechanical testing, and more. So the audio tests need to integrate seamlessly with these other tests. There are many different aspects of choosing and implementing an end-of-line audio test system. In this seminar, we're going to focus on 5 main areas: what to measure, the equipment, the software, hardware, and test fixtures you'll need to make audio measurements, optimizing your test. Here I'll share with you the things that I think are important in making sure your test is fast, repeatable, and accurate with appropriate limits. Integrating your audio test with the overall test environment. Finally, test specifications and security. Production line tests measure overall performance parameters such as frequency response and THD to ensure that the devices are within specification. They also make measurements to identify manufacturing errors such as reverse polarity, rub and buzz, and loose particles. Let's review the most common measurements. Frequency response is probably the best test of overall performance. If frequency response is outside the limits, it may affect the tonal balance and will probably not sound as intended. For example, this loudspeaker will probably sound kind of tinny at high frequencies. THD indicates overall nonlinear performance of the device. If THD is outside the limits, it may indicate a poorly centered voice coil or mechanical defects. For example, this loudspeaker has high second harmonic distortion, which probably is not audible until played at high levels. A polarity measurement verifies that lead wires are correctly connected and not inverted, especially for multi-way systems with crossovers. The main concern is low frequency cancellation due to the woofers being out of phase with each other. High order harmonic distortion, or rub and buzz, tends to be very audible, and it highlights a range of manufacturing issues, usually motor and suspension problems, such as an incorrectly centered voice coil, badly trimmed lead wires, or components not glued properly. Analyzing individual harmonics can give a detailed insight into the nature of the problem, as well as a simple pass-fail result. For example, odd order harmonics are a lot more audible than even order harmonics. Perceptual rub and buzz measures the audibility of rub and buzz based on a perceptual model. This is a great metric to decide whether to ship a product, as it will reject only those with audible rub and buzz, resulting in a higher yield. Here, there's both conventional and perceptual measurements. I'm not going to go into a lot of detail today, but it's worth understanding both and the differences between them. For example, it is much harder to hear low-order harmonics than high-order harmonics. We have a separate video on our website that goes into more detail on perceptual rub and buzz theory and practice. Loose particle measurements are a time domain measurement that identifies speakers with small particles such as dirt, glue, and magnetic chips trapped inside the voice coil or under the dust cap, or rattling components such as buttons and fasteners. Unlike harmonic distortion, which can actually make the speaker sound warmer, transient distortion will always sound unnatural. Impedance checks for resonance to ensure correct magnetization and mechanical tolerances, for example, spider, cone, voice coil, and so on. If the resonant frequency is too low or too narrow, the speaker may sound boomy and bottom out faster at higher sound pressure levels. You may also evaluate additional parameters, but these core measurements will likely be at the center of your audio test, whatever your device. So now we know what we're measuring. Let's look at our test equipment. Production test systems are typically less expensive and more basic than what you use in R&D. Some manufacturers promote a separate low-cost system for end-of-line test, but we prefer a modular approach to both software and hardware. This provides seamless compatibility between manufacturing and development, and it means that we can offer a suitably low-cost system for production and a more advanced feature set appropriate for R&D. The other benefits of this is that you can create and modify tests in the lab and send them to production for implementation, or send production line results back to the R&D lab for further analysis and troubleshooting assistance. Modularity also future-proofs your system. You can add a new digital interface such as Bluetooth or A2B, increase the channel count, or add new capabilities if you need to expand your capabilities for new products. A test system generally consists of both hardware and software. Measurement microphones to capture the sound, an audio interface to send and receive waveforms to and from the computer, and software to analyze the measurements. Of course, you also have additional test fixturing depending on your product. But that's so highly customized, I'm not going to spend a lot of time talking about that here. There are two really important factors when choosing an end-of-line test system. First, will it get accurate results in your test environment? And second, does it have the flexibility you need to customize your test now and in the future and integrate with your wider factory automation systems? Although many products promise broadly similar measurements, they don't all feature the same accuracy, speed, immunity to background noise, and calibration capabilities. This is also where I often see problems with homegrown systems. They can produce a frequency response and THD measurement with a slow sweep in a quiet lab, but put them on a noisy, high-throughput production line with different interface that is not accurately calibrated, or worse, simply not suitable for audio test, and it can all go wrong very quickly. Let's start with measurement accuracy. For accurate measurements, a good signal-to-noise ratio is essential. The noise floor of each individual component in the system must be lower than the background noise and dynamic range of the device under test. For most transducer measurements, either a professional audio interface or a specific audio measurement interface usually offers ample headroom for accurate audio measurements as long as there is appropriate gain to maximize its dynamic range. You also need to ensure that the frequency response and sampling rate is sufficient to test your device. Generally speaking, your bandwidth must range from 1 octave below your lowest measurement frequency to the highest harmonic that you need to measure. Otherwise, high-pass and anti-alias filters can cause inaccurate measurements, especially for phase, at the upper and lower frequencies. The sampling rate should be more than double the maximum frequency that you need to measure. It's important to know that the higher the sampling rate, the more memory and disk space you will need. So you'll probably want to use the lowest sampling rate that will meet your needs. It's also important that the frequency and phase responses are stable and flat enough that it is easily corrected for in the software. We typically suggest an audio interface with an ASIO driver for consistent and repeatable latency. Good signal path calibration of microphones and mouse simulators is also essential for accurate results. In SoundCheck, we do this through the hardware and calibration editors. What's nice about this is that you're calibrating the entire input or output signal path on a system level. This avoids the need to calibrate each device separately, and signal path calibration is quick using the software's self-calibration test sequences. You can store and recall multiple calibration paths for different channels and configurations. The software algorithms themselves also play a significant role in measurement accuracy, and that's down to the expertise of the developers. Over the years, we've invested a lot into creating algorithms for end-of-the-line tests that perform accurately at high speeds and algorithms that offer repeatable measurements in the presence of background noise. You can read the AES papers about these on our website. As I mentioned previously, for accurate measurements, you need a good audio interface with sufficient bandwidth, resolution, stable latency, and a low noise floor. There's always a debate about whether you should use a complete system, including hardware and software, or use software with a third-party audio interface. I always say, do what's best for you, provided your system can support it, which of course SoundCheck can. If you're not familiar with SoundCheck, it works with a wide range of audio interfaces, but we also offer our own, which integrate tightly with the software and offer many advantages, especially for a production environment. While Pro Audio sound cards are often the cheapest option, especially for high channel counts, they do have some drawbacks. Common pain points with sound cards include signal path calibration. To get accurate measurements, you must be able to calibrate all your signal paths from the beginning of the signal chain to the end. For example, not just the microphone, but the microphone, preamplifier, gain, and analog to digital converters. Not all software allows all signal paths to be calibrated, and not all sound cards can be easily calibrated. So this is something you need to check. If you do use a sound card, I highly recommend taking advice from your software vendor as to what devices they have qualified. They know a lot about what works and what doesn't. Cabling errors. Audio interfaces usually have to use a lot of cables. It's easy to connect something up wrong or to have a faulty cable or loose connector. Accidental adjustments. Pro Audio sound cards have many front panel controls, including gain adjustment. You can probably imagine what happens to your measurement if your gain knob is accidentally changed midway through a production run. It's not a big deal when you only have one sound card to set up, but if you're configuring 30 or 40 production lines, it takes time to configure the channels and calibrate everything. And you can't rush this. Your test integrity depends on this being done correctly. A dedicated audio measurement interface often provides a better solution. These are our AmpConnect 621 and our portable Audio Connect 2 audio interfaces. These are rugged and rack mountable and connect to a computer via a single USB cable. All the signals are routed internally, so we eliminate a lot of the cabling issues. This keeps your setup simple and reduces the possibility of unplugged or incorrectly connected cables. There are no knobs on the front panel or back panels that could get knocked and mess up your calibration. They are entirely controlled by software. Their input channels, this one has 2 and this one has 6, offer both constant voltage and constant current power for measurement microphones, and they also offer TED support. They both have 2 output channels, and the AmpConnect 621 also has an amplifier to drive a passive speaker or an artificial mouth, and has patented sense resistor in the feedback loop to measure current and calculate the speaker impedance in our software. When you combine multiple components into one interface like this, it's not only cost effective, but you cut down on cabling, and that avoids a lot of potential sources for error. The other really neat thing about these interfaces is that they really are plug and play. The calibration data is stored on the device's firmware, and SoundCheck reads the calibration values automatically when it is connected. There is no need for manual calibration. The input channels also automatically populate with sampling rates, and the device self-test requires no additional cabling, as all switching is internal. If you're using TED's microphones, you can also automatically read this data too. This offers huge savings in setup time, particularly if you have a lot of systems to configure. Because all control is via the software, you have much greater control over your test. You can set the hardware configuration as part of your test sequence, including gain plus auto ranging, which is hugely important for measuring low distortions like rub and buzz, as well as preventing overload. It also means that no one can mess up your calibration, either by adjusting knobs or by incorrectly setting it up in the first place. This ensures that your test is being run correctly, and is particularly useful if you're relying on third-party manufacturers to run your test. If you specify the hardware, software, and test sequences, you can significantly minimize the chances of measurement errors. Moving beyond the immediate test equipment, the next thing you need to think about is test boxes or chambers and fixturing. I'm not going to spend a lot of time on this as every situation is different. Production lines are inherently noisy places. 80 dB SPL or more is common, especially at low frequencies, and you get a mix of continuous noise like machinery hum or air conditioning, and transient noises like air compressors and stamping machines. These often mask production line defects. It's easy to get a speaker with no rub and buzz to fail if the test box is not well sealed and background noise gets measured instead. In the case of loudspeaker, you'll need a well-sealed test box. Try measuring the factory noise inside the test box with the same microphone that you will use to measure the loudspeaker. Compare the loudspeaker's distortion spectrum to the factory noise spectrum. Is the distortion spectrum above the factory noise spectrum? If not, you need better isolation. A headphone test might use a coupler or customized test jig, also in a noise isolating box. You want to think about how the fixturing might affect the measurements too. For example, if you're testing speakers, you want to point the driver down to increase the probability of detecting voice coil offset or loose particles that may hit the dust cap. Your microphone should be in the near field, but not too close to the speaker, to minimize both test box and fixture reflections and maximize your signal to noise while still getting a repeatable high-frequency measurement. There are lots of companies out there making both standard and custom test boxes that work with factory automation, so it's really a case of designing something that works for your products and ensuring you understand any effect of the fixturing on the measurements. Now I'm going to talk a little bit about configuring and optimizing your tests to make sure you get accurate results. Production tests are always a trade-off between speed, accuracy, and thoroughness. This means it's important to understand how to optimize a test to make sure you're getting reliable results. I'm going to use a loudspeaker as an example, but the same principles can be applied to any product. First, you need to ensure you have a good enough signal-to-noise ratio. The safest thing you can do here is to use a single sweep at a high level. Just be careful about the level if adhesives in the device are not fully cured. The test stimulus should excite the loudspeaker over its useful frequency range and should also cover the frequencies about an octave below the loudspeaker's fundamental resonant frequency. I always recommend sweeping from high to low frequency, as this applies a more gradual increase in power to the loudspeaker and reduces loudspeaker ringing and measurement settling time. This means you can use a faster sweep to reduce the test time. In terms of a test signal, I'm a big fan of the sweep. This is our optimized step sine wave sweep. It's been optimized for speed, noise rejection, and accuracy, and it can be as fast as a log chirp and even sound like a log chirp, but without the added complexity of time windowing. Let's take a listen. Time windowing results in linear frequency resolution, which can be misleading, especially at low frequencies where there is not enough frequency resolution. The sweep can also be used for perceptual distortion measurements in the same sweep as conventional measurements and impedance. The other things that we can vary to optimize our test time are the speed and resolution of the test signal. Everyone wants fast throughput, but if you sweep too fast, you can miss problem areas, such as a high Q resonance causing distortion. What I'm going to show you now is one of SoundCheck's best kept secrets. We actually have a function called measurement confidence, which helps you fine-tune your test to ensure that you don't sacrifice accuracy for speed. You can find this in the harmonic track analysis editor. What I generally recommend is that you measure first with a slow, high-resolution sweep, such as 1/24th octave steps and 24 cycles or 10 millisecond averaging time. You can then decrease the averaging time while monitoring the measurement confidence. This is particularly important for distortion measurements, such as rub and buzz, that require a wide dynamic measurement range. You can then decrease the frequency resolution and overlay it with a high resolution measurement on the same graph to see if the speaker's frequency response changes noticeably. You can also tweak the stimulus to minimize the effects of background noise. I like to use a custom step sine sweep. This optimizes stimulus time by using less frequency resolution and longer averaging time at lower frequencies, where the response is smoother. At higher frequencies, where the response is less smooth, it uses more frequency resolution. So you can see how valuable this tool is. It tells you how reliable your measurement will be as you vary your test conditions. In fact, this is the first thing I advise people to check if measurements do not correlate to what they are hearing. Just be aware that it might not always tell you what you want to hear, particularly if you have a lot of background noise. As far as I know, we are the only company to offer this functionality. Sometimes you hear people talk about using an external ambient microphone for detecting background noise. It's actually much more useful to use the measurement confidence feature in SoundCheck. This measures the signal-to-noise ratio at the actual measurement microphone position to predict how repeatable your measurement will be, rather than the noise outside of the test box. It also avoids the cost of an extra measurement microphone and channel. Of course, although it's always worthwhile optimizing your test speed, it's important to remember that the majority of the loudspeaker test cycle time is due to loading and unloading the loudspeaker, especially when this is done manually. This can be decreased by automatic positioning and connections or measuring one loudspeaker in the test box while another is being loaded or unloaded. Limit setting is perhaps the hardest part of production line testing, yet it's critical that it's done correctly. Production tests are hard to correlate with R&D measurements as test conditions are different, so we usually compare a production unit to other units measured on the production line. There are two ways of doing this. You can compare your measured speaker to a reference standard, sometimes called a golden unit, or you can compare it to a statistical average of good units. Both methods are acceptable, but there are trade-offs. When you measure to a reference standard, a golden unit is selected, and all measurements are compared to how the speaker measures on any given day. This means that the test environment, temperature, humidity, measurement chamber, and test jigs have no influence on measurements since they are all relative to the reference standard. Golden samples must be carefully chosen. Often it's the best fit to mean from a batch of good units. The method for choosing, as well as how to handle any changes in the golden sample, should be well documented to ensure consistency. Samples must be carefully stored and requalified periodically, for example, at the beginning of every batch or shift. The disadvantages to this method are the reference loudspeaker can deteriorate and drift over time, and after a while, it needs to be replaced with a new reference loudspeaker. The alternative is measuring to absolute limits. In this case, you use verified or approved samples to set limits, but once they are determined, the samples are not remeasured. While this is simpler than using a golden unit, the environment must be well controlled and test tools and measurement equipment well maintained, since any change in these will affect the absolute measurements. Setting absolute limits is not straightforward, and a significant number of speakers, all conforming to specification, is required. For each performance characteristic, except rub and buzz and loose particles, the average, standard deviation, and the process capability for the batch of speakers must be calculated. A good starting point for all curve limits, apart from rub and buzz, is the mean curve plus or minus 3 sigma, or standard deviations. Distortion limits are a little different. For THD, a plus 5 sigma limit is a good starting point. Rub and buzz limits are manually set to levels such that they always reject audible distortion. Limits may need to float in both level and frequency to overcome reflections from fixturing and from the test box itself. When configuring limits, devices should be measured multiple times for gauge R&R to understand any variations in the product measurement positioning and to ensure measurement repeatability. There is often a certain amount of trial and error involved in setting limits, tweaking them until there is acceptable yield and good correlation with human listeners. Correctly setting limits is an extremely complex process, and it's well worth being on site to assist with limit setting when you are putting a device into production so you can truly see and hear what is going on. Otherwise, make sure the production operator saves the calibrated, measured, recorded waveforms from the test system for you to listen to and analyze offline. The good news is the new perceptual algorithms, such as enhanced perceptual rub and buzz and enhanced loose particles, are simplifying limit setting. Both our perceptual rub and buzz metric and our new transient distortion measurement method offer a simple flat limit correlated to audibility, and since it's based on audibility, it'll even be the same across multiple products. This simplicity makes these measurements extremely fast and simple to configure. Finally, while I'm talking about the test configuration, don't forget the importance of calibration. Any measurement is meaningless if your audio interfaces and signal paths are not correctly calibrated. You can't leave anything to chance here. When you're setting up a production line, it's critical to calibrate and regularly recalibrate all signal paths. Of course, calibration procedures and frequencies should be fully documented, and just in case you didn't know this, you can always check your calibration history in SoundCheck. So that's the basics of optimizing your production line audio test. Now let's talk about how you can integrate your audio test system with your overall factory environment. I mentioned at the beginning, it's important that any test system you are considering has the flexibility you need, as well as the measurement capability. That's where the ability to integrate with the rest of your test environment is important. Over to my colleague Mark Latshaw, who will explain in more detail.
Thank you, Steve. Manufacturing test systems often need to be integrated with larger factory automation systems for both collecting and saving data. Let's start with saving data. When you specify a test system, you need to think about what data you need to collect and maintain, both now and in the future. Sometimes, a real-time pass-fail result is sufficient, but it's becoming increasingly common to save all test data to a database for further analysis and statistics. We're even seeing cases where contract manufacturers are required to automatically save all their test data to the OEM's own database for full traceability. Everyone wants to manage this differently, so in SoundCheck we offer several different options. Directly in a SoundCheck step, you can save your curves, values, or results to a database. Using an autosave step, you can make a connection to a Microsoft Access or SQL database so that whenever your sequence runs, the data is sent to the database. Industry standard tools can then be harnessed to run analytics over large data sets. For example, a database query can be created to average the frequency responses on all measured devices and create limits based on that average. Even if you're not using a database, SoundCheck still has options to get your data into a format that's easy to work with. In addition to the options shown directly in the autosave editor, text, CSV, Excel, TDMS, MATLAB, and more, there's also a plugin available to transfer data to Varenko's Watts Test Data Management platform. Recently, we've added the ability to also save metadata when saving to TDMS. Metadata includes system data, such as the sequence name, serial number, or operator. User-defined fields can also be added to track test conditions such as temperature, humidity, microphone distance, test configuration, and more. You can even include the recorded waveform in a TDMS format. Data is saved extremely fast in this format, so although it captures a lot of information, it doesn't slow down your test sequence. This data can be viewed or recalled in SoundCheck and also opened in other applications, such as Microsoft Excel, MATLAB, and even Watts using a plugin. For more customized configurations, all the data saved in SoundCheck's memory list can always be accessed directly via TCP/IP. This means you can write your own customized program to collect exactly the SoundCheck data you need. Simply read the memory list items using a TCP/IP connection to the SoundCheck computer, and you'll have all the measurements ready to go in your own program. We have some very basic examples of this included with the SoundCheck installation in the external control examples folder, but the final product can be as specific to your use case as you need. Saving data is only one part of factory integration. You also need to consider what level of test automation you require. Tests for simple products, such as drivers, microspeakers, and earphones, tend to be fairly standalone, but for more complex devices, audio tests are often one small part of a larger test plan. In these cases, screen tests, connectivity checks, and other inspections may also be made alongside the audio measurements, and the audio tests might be controlled by a larger test automation system, such as TestStand. Since SoundCheck 15, we've also included TCP/IP control. This provides ultimate flexibility, as you can control it in any programming language that can provide TCP/IP commands, such as Python, LabVIEW, C, and more. These commands may not only start and stop tests, but also import data stored outside of SoundCheck. One way that you might want to use this is if you run similar tests on multiple products, but the specific parameters are different depending on the product. If you use TCP/IP control, you can automatically pull in the limits based on a target curve, start and stop frequencies, or the appropriate test level for each specific model. This avoids having multiple versions of the sequence that need updating, and makes it quick and easy to add tests for additional products. It can also be used, for example, to output a command to a sorting device on a production line that matches components based on test characteristics or sorts into pass or fail bins. TCP/IP control has the potential to streamline your manufacturing process and minimize sequence updates. Although it requires a little effort to implement, the payback is huge as it lets you integrate professional audio testing with all its advanced techniques and algorithms into your highly customized test environment. It's not only the big things like saving data and controlling SoundCheck that make it easy to integrate into your production environment. You can use a system step, LabVIEW custom VI step, or a custom Python step in any SoundCheck sequence. The system step allows you to send input directly to either the command prompt on Windows or a terminal on macOS. For example, this could be used to run a batch file to set your device into diagnostic mode. The LabVIEW and Python steps let you expand the capability of SoundCheck in absolutely any way that you want, through either LabVIEW or Python commands. For example, you could write a Python script to create a function that isn't available in SoundCheck, and then use it as a step in SoundCheck. Memoryless data can be sent to the script, have a function applied, and that new processed data can then be sent back to SoundCheck. For example, we include a Python script with SoundCheck that will check a pass or fail criteria against a limit, but will only fail if 2 consecutive points exceed a limit. That same process could be done in SoundCheck, but might take a large number of steps. This script is placed as a single step in your sequence. Curves are passed into the Python script, it executes, and the pass or fail result will be returned to SoundCheck. Finally, let's talk about production test specification and security. It's easy to lose control of your audio tests when you're outsourcing your manufacturing to another country, sometimes even a separate company altogether if you're using a contract manufacturer. Over the years, we've seen many production facilities and contract manufacturers, and there's a vast difference in how quality-driven and knowledgeable they are. Some will take quality very seriously, but I've also heard stories about others who will leave test boxes open because adding noise to the measurement gets a higher number of devices to pass the distortion test. But it's not always this intentional. Some manufacturers use homegrown or low-cost test systems that simply do not get accurate results. Sometimes, engineers pair a software-based system with an inadequate audio interface, for example one that is too noisy, or has phase issues that lead to incorrect measurements. You also need to be aware that sometimes when manufacturers tell you they're using a well-known test system, they may actually be using a pirated version. Those have a whole host of problems, including security issues, older versions of the software without the latest algorithms, lookalike or imitation products that simply do not measure correctly, and of course, lack of manufacturer support and upgrades. Tight control of your test process can mitigate a lot of these problems. The first place to start with is your test specifications. The more tightly you specify your tests, the more consistent and better quality your end product will be. Since manufacturers are focused on yield and profitability, they have little to gain by testing more thoroughly than the terms of your contract dictates, so the burden is on you to be specific. There is a big difference between requiring frequency response within 3 dB of golden unit and specifying frequency response within 3 dB of the golden unit, measured at the start of each batch in a well-controlled test environment using SoundCheck version 22 and Audio Connect 2 running this provided test sequence. At the very least, it is advisable to fully specify the software, down to the current version number and the hardware configuration that is required to run all your tests. You should also specify the authorized vendor from which they must buy it. Many large OEMs have gone one step further, purchasing it themselves for their contract manufacturer to guarantee system integrity. If you are relying on your contract manufacturer to purchase the software, it is a good idea to request the serial numbers of the systems they plan to use on your lines and verify their authenticity with the manufacturer. Hardware is also important, and this is another place where ignorance can sabotage your measurements. It's critical to use an audio interface with sufficient dynamic and frequency range, and it is also important that it can be fully calibrated with the software. Many times, I have seen a manufacturer spend good money on a professional audio measurement system specified by the OEM, only to then save money by pairing it with a low-cost sound card that isn't good enough to get consistent results. It doesn't have to be the same interface that you use in the lab. There's often a cheaper alternative that will be adequate for production testing, but do take the advice of your system provider and ensure that the hardware is also clearly specified in your test plan. These days, most quality-driven OEMs provide their manufacturer with the specific tests that need to be implemented. They're easily shared via email, network, or USB drive. Bear in mind that even with a test sequence, your manufacturer will still need to calibrate, and if limits are relative, will need to understand how to set limits based on a golden unit. So clearly written procedures are invaluable. This brings us to documentation. Document everything. This may seem like common sense, but specific, clearly documented operating instructions will improve your test integrity. You should cover everything from initial system configuration, wiring diagrams, and daily system test and calibration directions to precise instructions about positioning, fixturing, and procedures for a failing test. If you are providing test sequences to your manufacturers, it's easy to supplement standalone instructions with text, diagrams, photos, or even video instructions within the test sequence. This can help, for example, with ensuring accurate positioning and other operator interaction during the test. Knowledge transfer has been extremely challenging over the last few years due to travel restrictions, so it is more important than ever to ensure that all production test operators are adequately trained and have strong supporting documentation. There's a couple of new features we've added in SoundCheck to help maintain security and control of the entire test procedure. Measurement sequences can now be locked and protected. A protected sequence can't be viewed, opened, or modified without a password, so it provides complete test confidentiality and security. It can only be implemented exactly as written, without modification, and it cannot be copied or recreated for use with other products. Test sequences can also be locked to specific SoundCheck serial numbers to ensure that all measurements are being made on legitimate SoundCheck systems. If you have any doubts at all about the test systems that your CM might be using, this is a great way to be sure that the systems they told you about are up to date and are actually being used on your lines. We've also just added sequence versioning, which allows complete tracking of any sequence modification. This also helps ensure that your manufacturing facility is always using the latest approved version of a test sequence. I'm going to hand back to Steve now, who will talk about compatibility between R&D and production.
The last thing we're going to talk about is compatibility with R&D. When R&D and production both use the same platform, even if one is a more advanced system than the other, you get a lot of synergy. It's easier to train people, you can easily move tests from R&D to production. R&D personnel can assist with production setup and detailed analysis or troubleshooting of production line results, and more. I talked about modularity earlier. This is another place you can see the benefits of this approach. You can configure, for example, a test system for production line headphone testing that uses an inexpensive 2-channel version of the software with a fairly minimal group of analysis modules. For hardware, you could use a 2-channel audio interface to power your microphones or couplers and your own custom test jig or couplers. This contrasts with what you might have in the R&D lab for headphone development, where you might need to implement extensive tests involving directionality, background noise, ANC, and more. Your test setup there might include a head and torso simulator, a turntable, and background noise generation. You'll likely need multiple input and output channels and some advanced software features such as polar plotting, the equation editor for defining your own custom calculations, and more. And a system like this might run to 2 or 3 times what the production system cost. The hardware can be expensive too, although SoundCheck will work with any audio test hardware. For example, head and torso simulators from B&K and Grass, turntables from Portland Tool and Die, Outline, etc., and microphones from most vendors. So this means you can often save money if you already have these in your lab. Of course, whether it's an R&D system or a production system, if your needs change, it's easy to add additional capability, whether that is software functionality or, for example, a new interface. You can even upgrade from a production system to an R&D system simply by paying the cost difference. This means that with minimal configuration changes, you can test raw drivers, speaker systems, smart devices, soundbars, headphones, hearing aids, automotive audio, and more across production and development, all using the same test platform. So as you can see, end-of-line test is a complex subject with many considerations to take into account. Hopefully you found this overview useful in figuring out the important things to look out for when you're configuring a production line. Let's just summarize. First, you need to understand what characteristics you need to measure and select the right test equipment. You should select test software that not only makes the measurements you need, but that is also fast enough for your needs, accurate in your environment, providing repeatable results with your level of background noise, communicates adequately with your factory automation and database, is flexible enough to grow with your future needs, and select test hardware that offers a low enough noise floor and sufficient sampling rates for the products you need to test, permits accurate signal path calibration, is simple to use, for example, self-calibration, minimal cabling, leaves no room for error, for example, knobs that are easily knocked, is suitably rugged for a factory environment. Next, optimize your test. Optimize your test stimulus for the best trade-off between speed and accuracy. Minimize your background noise with the right test environment. Use measurement confidence to help you fine-tune your measurements. It's critically important to understand limits and configure them carefully, and also ensure that any contract manufacturers you might be using are well trained. Consider perceptual algorithms for easy limit setting and better correlation to perceived quality. Finally, document everything. Thoroughly document all test procedures. Clearly specify test equipment. The more detail, the better. Protect your investment with advanced test system functionality, such as sequence protection and versioning. Thanks for watching. I hope you found this helpful. Please check out our website for more information on all of these topics discussed in this video.